Everyone, welcome to the first distinguished talk this year after a long break caused by the pandemic. So we are very happy to have Professor Omer Reingold here. So Omer is a professor. He is the Rajiv Motwani Professor of Computer Science at Stanford, and also the director of the Simons Collaboration on the Theory of Algorithms Fairness. So Omer has made numerous important contributions to the foundations of computer science in various areas like pseudorandomness, complexity theory, and cryptography. So most notably, he was awarded the 2005 Grace Murray Hopper Award for his work of proving that the symmetric log space is the same as log space, and also the 2009 Godel Prize for his work on the zigzag graph product, together with Avi Wigginson and Salil Vadan. So again, we're very happy to have him here today to give us a lecture on new concepts in algorithm fairness. So without further introduction, let's welcome Omer.
Thank you very much for the introduction. And let me see. I'm trying to share my screen. Good. Do you see that?
Yeah, we can see that.
Perfect. Thank you. So thanks again for the lovely introduction. And I should start with an awkward confession. I'm actually not an expert on karma. I haven't done research on karma, and this was mainly to bait you here. And I know that it's not the most ethical thing to do. So let me quickly, without you noticing, replace it with a more respectable title, Multicalibration and its applications. But hopefully you'll find some reason for which my original title was reasonable. And I want to say that this is shared work with many other collaborators, great collaborators listed here, and also represent some of the work of this community, which includes many others. So when we're doing, by the way, I'll welcome questions throughout the talk, and if there are questions in chat, and if one of you can read them to me, because I will not be able to monitor the chat. Okay, so I think it's really important when we're doing some work to understand what are the assumptions at the basis of this work. What are we implicitly assuming? And I'll just let you know here immediately what is it that I'm assuming. And we can argue on many of those things. We can give entire talks about many of the things, but I want to tell you what's the assumptions I'm making in this particular talk. So, so the first one, I think we will all agree that algorithms are making or informing decisions all around us. So especially machine learning algorithms are really all around us, making predictions about us, classifying us in various ways, and it is in medical diagnosis, employment, in decisions of whether we are incarcerated or not, who we get to date, soon how our cars are driving. Okay, so I was very excited about the dating thing. I have it twice. What are the ads we see? What is the content we are exposed to? And I think at this point we also understand that algorithms is not these objective creatures that that do everything impartially. There is nothing particularly objective or subjective about algorithms. Algorithms are created by humans and rely on human design choices. And in the case of learning, they also rely on historic data, which incorporates various biases that already exist within our populations. And given that algorithms are making all of these decisions or informing all of these decisions, that that are very important to our lives. There are a host of ethical questions that come through that, and a lot of concerns. And today I'm going to focus on the concern that algorithms will unfairly discriminate against some humans or some subpopulations. And this is really by now not an hypothetical concern. It is a real concern. This bunch of images I stole from my ex-student Michael Kim, but there are many more of the best companies, the most advanced companies, failing again and again on issues of fairness. And this is by now part of popular media, and the concerns are rising and really risking the confidence of the population in this revolution that we are part of. Also, we should note that algorithmic fairness is not something that computer scientists should solve by their own. It is a multidisciplinary area. It has been studied. Fairness definitely has been studied by many other fields for generations. And it is also part of the non-academic world, part of policy in policymakers, part of activism. It comes in industry. But still, our assumption here is that computer scientists need to be part of this effort. And as a field, I'm not saying that every individual has to, but as a field, we have an obligation to contribute. In some sense, we are part of the problem, and we should be part of the solution. And the final kind of assumption is that theory has an important role to play, and it has been playing for the last decade a very important role in these algorithmic research studies. And the things we provide best are models, definitions, algorithms. And in that, we are trying to follow the examples of other fields that where theory had major contributions, like cryptography, privacy, algorithmic game theory, and others. Okay, so that's all the assumptions. I hope that that you find them reasonable. But in any case, this is what leads to the research I'm going to talk about. And I'll start with a very short kind of overview of some of the algorithmic fairness definitions that have been proposed for more than a decade now. And this will lead us to this notion of multicalibration. And then I want to say, or to share with you, 3 different applications of this notion that really surprised me. It wasn't really part of what was planned when we came up with multicalibration. And this is a very ambitious plan, so I don't know to what level I'll be able to carry it out. But I hope to tell you a little bit about these 3 different applications where something interesting happened. So the first one is this notion of outcome indistinguishability that gives a computational perspective on the meaning of individual probabilities. Omnipredictors that kind of give an alternative to this paradigm of loss minimization, the standard paradigm of loss minimization in machine learning, and universal adaptability that is kind of an alternative to this idea of learning propensity scores. Okay. So with that, let's make our talk a little bit more specific and tell you, I mean, there are lots of algorithmic tasks, and for every algorithmic task, we can ask what are the fairness concerns that we need to address, what kind of definitions. We will focus here on one task, an important task, which is prediction. So the moment we go into the world, algorithms are measuring us all the time for various reasons. So what's the probability that we're going to click on an ad or an article? And what's the probability that we are going to have a heart attack within the next 10 years? What's the probability that we are going to repay a particular loan? And all of these predictions of these probabilities, or we'll talk what do these probabilities mean, then inform decisions, so inform classification. Are we going to see this ad? Are we going to get this particular rate for our life insurance? Are we going to get the loan? So how do these risk scores, predictors, come into the world? Well, like many other things today, it comes through the magic of machine learning, and which is kind of a meat grinder. What you get is you put in data, which is historic data. So for example, previous people, medical medical data, and whether they had a heart attack within 10 years from when the data was collected. And then we are going to fit some model, kind of minimize some loss, optimize some objective, and spit out this model that is able to calculate some numbers for every individual that should represent these probabilities. So, so this gives us the predictors, and now for every individual that comes, we kind of feed the information of this individual to our model, and we get a number that should represent the probability of a heart attack in 10 years. So this is a predictor, and it also gives us then, or often is used for classification. Will we get this life insurance, or which premium of a life insurance we're going to get? So this is the model. And since we said that discrimination is a concern, then we want to define fairness. And how would we define fairness? Whenever I tell people I'm working on algorithmic fairness, they ask me, okay, what is algorithmic fairness? What is fairness? And the problem is, or the issue is, or the challenge, or the opportunity is that we cannot expect a single definition of algorithmic fairness. There isn't a single definition that tells us that, and there isn't and couldn't be a single definition that would tell us if an algorithm is fair or not. The issue is that fairness is complicated. We have been observing over the years that discrimination can be very subtle. There is a catalog of evils you can use for discrimination, for unfair discrimination. And you can not even hope for an optimal definition that would have all the things that we may want, because natural notions are in conflict. You cannot get all of them together. So there are inherent trade-offs. And therefore, we need to understand that fairness is context dependent and should incorporate social norms. What is fair in one setting is not fair in another setting. And it's more a choice than anything else. Nevertheless, even in that perspective, theory is crucial. And it is because all of these fields that I mentioned that want to deal with fairness may help us define kind of what are the aspirations, what we want our algorithms to satisfy. But if we want to turn it into algorithmic realities, we need definitions. Another thing is that it's better to argue about definitions rather than about systems. Again, following the example of cryptography, instead of having a system and breaking and improving, breaking and improving, or arguing, is it fair or not? We have a definition. We can argue, do we like this definition or not? It's much better because we can then know if now the new system that we are building is better or not. And also theory can provide trade-offs that were not previously existing. There is an example in privacy, which is differential privacy, which I won't discuss, but if you are not aware of it, I would definitely recommend it. So the way I view what we are doing here in theory is that we are providing a language that helps us discuss algorithmic fairness. And it is as important because this is a computational world, it's a notion within a computational world. This computational language is as important as the language that we get from other fields, perhaps more established, that have been talking about fairness. So more specifically, the most prevailing family of notions of fairness is these group notions of fairness. were a few protected groups, perhaps defined by race, ethnicity, gender, age, and other characteristics. For a few of those, we want to make sure that some overall parameter is the same on this protected set S and the general population. So somehow our predictors behave similarly on both. And there are many, many ways in which we can define what is similarly. For example, statistical parity would mean that the probability of a positive outcome according to these predictors are the same for S and outside of S. Calibration, we'll talk about more. It's some notion of accuracy. Balance talks about equalized false positives and false negatives. The advantage, and this is why these are prevailing notions, is that they are very easy to work with. And much of the literature talks about them. And this is very unfortunate because these are very weak. It's very easy to abuse all of these notions. They guarantee very, very little. And we've been observing it for more than a decade. And we are also seeing that some of them, enforcing them because they are so crude, may cause even more harm than good. They are at odds with each other. That's what I mentioned before. You can get all of them together. And they are also in odds with utility. And that led us about a decade ago, so Dwork, Hart, Pitassi, Zemel, and myself, to suggest a different notion, which is an individual notion of fairness, trying to get some guarantees per individual, not for in general for groups, formalizing this idea that similarly situated individuals should be treated similarly. And I'm putting it here just that you know that kind of there is a range between individual fairness and group fairness. I won't be able to talk about individual fairness here. Instead, I will talk about a new family of definitions that we call multi-group fairness from the last 3-4 years that has had a lot of impact and somehow stands kind of somewhere in the middle between these two notions and tries to get a little bit of the benefits of both. So this comes into the question of which groups. When we're talking about group fairness, the question that comes is which groups are we going to protect? And these notions give a computational perspective of which groups we're going to protect. And the thing is that often the weakness of group notions of fairness is that they do not protect important subgroups of the groups you are trying to protect. So here is an example again from this decade-old paper of Dwork et al., where we want to advertise a burger joint. And what we do, but we want to exclude a group S, which is protected. But of course, this is perhaps illegal. So what we're doing is that we are showing the ad to many people from S. So nobody can claim that we are not showing the ads to people in S, but we're showing to the wrong people. We're showing it to vegetarians in the group S, which will not come to our burger joint. And this way we are excluding S, although we are satisfying these assumptions. So fairness relies on identifying subgroups that are relevant to the task at hand, like carnivores in S in this example, or qualified job applicants in other examples, and treat them well. So I want to see that you're advertising for the carnivores in S, not just to vegetarians in S. The thing is that nobody would ever think about making carnivores in any group a protected set. And in a different application, it will be a different group. So we don't know a priori which groups we want to protect. And this actually also relates to kind of deep social understandings that even for protected sets, many sets do not, of individuals that are oppressed, don't always understand and are able to articulate that they are part of this group and this group needs to be protected. Definitely people from the outside are not expected to know that so well. So the question of which groups are going to be protected is important, and we actually see here that there should be many more groups than just the few that we define usually as protected groups. So multi-group fairness, which was introduced in parallel by Hébert-Johnson, Kim, myself, Rothblum, and Kearns, Neal, Roth, and Wu, offer fairness protection, some fairness protection, to a very large collection of sets. Essentially to any set, any large set that can be identified given the data that we have in front of us and given our computational limitations. So we're trying to protect whoever we can identify. In particular, yes, we can identify carnivores in S if that's some of the data we have. In some exact sense, this is the best possible. If there is a subset that we cannot identify, then we cannot protect it. Perhaps it means that we need to use more computational resources or to change our data, but that's our limitation. So this is an entire family, and I'm going to formally talk about multicalibration, but this is kind of the main object for this talk, and we'll have one slide of notation. Mostly could be ignored anyway, but just to be a little bit more concrete. So we have some population, and we have individuals selected from this population. Perhaps we have some distribution over these individuals. These are set, every individual is represented by some arbitrary set of features. And often they identify individuals, but it's not necessary for the definitions. We are trying to predict some outcome, the probability of a heart attack within 10 years, probability of repaying a loan. And in that, we are trying to, in this prediction, we are trying to look at this ideal notion that, of P star of X, which is kind of the true probability of this event conditioned on these set of attributes. We are trying to do it with a learning algorithm. The learning algorithm gets samples of individuals and whether the outcome happened or didn't happen for them in the past. And it produces a predictor P tilde, which should approximate this ideal P star. So P tilde is the algorithm's estimate of these true probabilities P star. P tilde of X is an estimate of P star of X. X represents an individual, let's say a patient. P tilde of X is supposed to approximate the probability that this individual is going to have a heart attack within the next 10 years. I want to say that this notion that I glossed over of P star of X is very problematic because, as I said, if X represents a single individual, then this probability represents something that's going to happen once. This individual is going to have a heart attack or not. We're not going to be able to sample it many times, and it's completely unclear what is this probability I'm talking about. And hopefully I'll get to the part in the talk where I'll tell you what kind of insight we can gather on that. But still, regardless of the fact that the real probabilities are something that we don't really completely understand, this is what machine learning algorithms are doing all the time, trying to predict probabilities and basing decisions, critical decisions on them. Calibration, which is a group notion, look at these predictors and try to force some kind of correctness guarantee. So the theory is that P tilde, our predictor, is going to downplay the fitness of S. And therefore, we ask for this calibration notion. So P tilde is approximately calibrated, alpha calibrated. This is some parameter on a set S. If for every prediction value, let's say 70%, if we look at the set of individuals, SV, which are all the individuals on which the predictor said this value, said, okay, there is 70% that these individuals are going to repay the loan. What we have is that on average, indeed, 70% repay the loan. This is just the math of this very simple notion. There is an additional subtlety here. Doesn't matter, you can ignore it. So essentially what it means that any prediction V on average means what it says. If we say 70%, 70% of the people for which we say 70% will indeed see a positive outcome. This is calibration. It's important because we are afraid of downplaying or the fitness of S. It's also important because when people use these predictions, you don't want them to reweigh your predictions. You want them to say, okay, these are the predictions. This is the best we have in front of us. This is extremely weak notion, like any other group notion, because one p tilde that would satisfy that is the p tilde which is fixed on S. It just gives every individual in S the average probability they have for a positive outcome. This is, I think, the definition of algorithmic stereotyping. You treat all of these individuals within S the same. This is a very weak notion. And this is where we want to improve it through this multi-group notion of fairness that we call multicalibration. So calibration is too weak, may discriminate against the qualified members of S. Multicalibration asks for calibration on a very large, very rich set of family of sets. So all the sets that are large and can be identified within some computational resources. So for a family of subsets C, P tilde is alpha multicalibrated on C if for every set in C, P tilde is alpha calibrated on T. So we want this weak condition, but not only on one set, on many possibly intersecting sets. Well, there will be intersecting sets. The way to think about C is the computational bounds. So C should represent everything that we have the ability to put our hands on. So for example, identifying if an individual is in a set T can be done by some circuits of some size, or perhaps more realistically in some cases, the conjunction of four attributes. So is this individual based on its the individual age, and whether they are carnivores, and their ethnicity, for example, would make a set. And when we show this work, we also show that it comes with algorithms, basic algorithms from the literature on optimization and learning can be adjusted to give us this multi-calibration. And what's very important is that you can obtain it in a post-processing fashion. So you can take your favorite deep network or whatever you produced, and if it's not multi-calibrated, you can turn it multi-calibrated. In fact, we've shown how it can really take care of some of the weaknesses of even sophisticated models pretty quickly. So this is this notion of multi-calibration. I want to discuss it a little bit before we move to its applications. I mean, is it fairness or is it accuracy? And indeed, multi-calibration is aimed to address additional discrimination by machine learning. Perhaps the data, the training data is already biased or represents some oppression, but we want to make sure that the machine learning algorithm doesn't introduce additional discrimination. So in this sense, it is talking about some fairness concern. I want to say that it can also serve more refined, kind of the basis of a more refined affirmative action. So the more we know about the situation as it is now, the better we can be in producing really refined affirmative action that really promotes the ones that are the best ones to promote. And I also want to say that multi-group notions come in many, many flavors, and some of them are really not about accuracy at all. They are about facilitating some sorts of social engineering, perhaps in the spirit of this fairness for awareness paper I mentioned in the past. But also I want to say that sometimes accuracy is exactly about fairness. And I'll give you an example from the healthcare, which is ageism. So often certain diseases in elderly patients are underdiagnosed. Also in other populations like obese patients, often they are underdiagnosed because these symptoms are masked as age-related symptoms. The risk is that a machine learning algorithm may choose to optimize on younger patients and may even increase this bias against older patients. On the other hand, we don't want to overcorrect. Sometimes these are really age-related symptoms, so we don't want to overdiagnose older patients with severe illnesses, which would lead to suffering in its own right. Sometimes getting the right values, not to overestimate and not to underestimate, is a form of fairness. Okay, so with that, I kind of, this completes kind of the first part, which I told you about the fairness side of this research. And now I want to tell you that this object, this multi-calibration in the last 3 years took off and really led to a lot of applications that at least I couldn't predict. I really had no intention to work on machine learning or anything like that. And I think there is some lesson in this story. So perhaps the less surprising thing is that multi-calibration, since it works, it deals with accuracy, actually could be the practical basis for learning in populations, like many populations that are heterogeneous. So it is less surprising. I still found it very surprising that it was actually practical, a theory idea, and I'll share it in a few slides. And then we are talking about these 3 general applications that I already mentioned before, and so I'll skip now, and hopefully I'll be able to describe all of them. We'll see. So I want to start with this idea that multi-calibration is practical. There have been several empiric studies that used multi-calibration to show improvements in data analysis. This one, for example, was a big study done by Clalit Research, Clalit Health Research Organization. Clalit Health is one of the biggest health providers in the world. I heard claims that it's the second. And they studied very well-established predictors that are used, for example, for various illnesses, and they had known problems that they were not really accurate on subpopulations. So they looked at subpopulations that are defined by combination of 5 attributes. So, for example, a population that can be a Caucasian female of a particular age range, of low socioeconomic status, and history of immigration. So a collection of variables. There are many sets like that. It's hard to learn separately for each one of them. And they showed that by a few steps of this post-processing, they really improved dramatically the correctness on all of these sets. So the yellow kind of represent the correctness on subsets to begin with. So yes, on average, this is calibrated, but for subsets, you see large deviations, and these well-established predictors in the healthcare systems take a long time to turn into something that's established and used by physicians. These well-established predictors have been highly inaccurate on subpopulations and very easily have been turned into accurate by this notion of multi-calibration. What was even more shocking is that the same organization used kind of in the field, but in a very rocky field, we're using these ideas to create a predictor of COVID-19 complications. What they did at the time that there were very little information, there weren't enough cases available in Israel to run a learning algorithm. What existed was a few group statistics that China shared, and what they decided to do, just to, for example, inform patients that they should take additional precautions, was to take a respiratory illness complication predictor, let's say complications of flu, and to try to post-process it with the group statistic that they got from China. There were lots of issues. Use the same algorithm from before, and in retrospect, it was quite successful. It was relatively accurate, even with no real data on or very limited data on the actual illness. So in heterogeneous populations, sometimes fairness can promote accuracy and utility because it helps identify untapped potential or unaccounted for risks. I could say that for me, this space, I mean, a work that had 2 years, existed for 2 years in theory, turning into a practical application is very exciting for a theoretician, but also very scary. So we like to have more time to play with our constructs. Okay, so now I have 3 applications to rush through. But as I'll tell you a little bit, each one of them would be a great thing to devote an entire talk to, but I want to share with you kind of this richness of notions. So the first result is outcome indistinguishability, joined with Dwork, Kim, Rothblum, and Yona. And it comes back to this question I asked before. What are those probabilities that we're talking about? The probability that the patient would have a heart attack in 10 years. This individual patient either will have a heart attack or not. It's not clear what is the probability on. And this idea of individual probabilities, I mean, it's not new. It has been debated for decades within statistics, perhaps longer in philosophy. And we're not trying to resolve it here. We're trying to give a new perspective on it. So this probability kind of try to capture some randomness in the environment, in nature. Perhaps we don't know everything about this individual. We have limited information. And given this information, there could be things we're unaware of. And also some bound on our computational resources. Even if we have all this information, we cannot run the world, simulate the entire world for 10 years and see if this individual has a heart attack or doesn't. The scale of algorithmic decision-making, which is really trying to answer this question, so machine learning is trying to provide these probabilities, really calls for a computational perspective on individual probabilities. If this is the products we are creating, what are they? What do they mean? And I want to give one tiny example that I borrowed from talks of Avi Vigderson when he talks about pseudo-randomness. And it says that randomness is in the eye of the beholder. It's very appropriate to some of the approaches come from statistics. So let's take the example of a random event, a coin flip. For us, it looks like a 50-50 event. Perhaps we saw this coin being flipped 100 times and we think that it was about 50 times heads or roughly and tail. So we think it's an unbiased coin and we think the probability is 50%. So P star is half. But if we take the same coin flip and we add lots of sensors that in real time give us information, which we connect to amazingly powerful computational devices, perhaps we can entirely compute if the coin is going to turn heads or tail within the first second when it's in the air. So for that perspective, there is no probability. It's either 0 or 1. This means that what we can observe is does determine our perspective on randomness. So without all of this information, we cannot really differentiate the coin flip that we see with a different coin flip where right at the end, somebody switches the coin with a really random coin. And we have come up with this notion that I don't have tons of time to explain of outcome indistinguishability that takes these kind of ideas into the notion of predictors. So a predictor P tilde gives a generative model for outcomes. We don't know what is really happening, what is P star, but P tilde tells us that this patient is going to have a heart attack with probability 10% and this one with probability 2%. So we can imagine a world where indeed there is some coin flips that tells us that operate exactly based on P tilde. So let's imagine this world, and in this world, the outcomes are not the real outcomes, but these O tildes. So when the predictor says 10% or 25%, and then somebody flips in the back 2 coins, and if it's 2 heads, then it's going to be they're going to have a heart attack. What outcome indistinguishability says that given specific computational resources, we cannot distinguish if our world operates like it does, the real outcomes, the true outcomes, we cannot distinguish them from these fake outcomes. So in other words, the generative model that P tilde provides to us cannot be empirically refuted with bounded computational resources. It kind of imitates this notion of the scientific method. And by giving some computational explanation of the meaning of individual probabilities. So this P tilde could be viewed as individual probabilities. They may be very far from reality. Perhaps in reality, there is no probabilities, it's zeros and ones. But given our information, we cannot distinguish it from reality. I want to say that outcome indistinguishability is closely related to multicalibration. There is some equivalence, and it shares insights about auditors. So if you want to audit predictors, we learn some interesting things. For example, that having access to the source, the code of the predictor could have a huge impact on our ability to have effective auditing. And this could have practical applications. So that's all I wanted to say about outcome indistinguishability, a new perspective, a computational perspective on the meaning of individual probabilities. I want to talk about a different application, universal adaptability, which is joint with Kim, Kern, Goldwasser, and Kreuter. And here we want to talk about adapting the outcomes of research from one population to another. So Stanford Hospital conducts an experiment, and for example, to determine the success rate of some health policy or some intervention. And we ask, can Princeton Hospital rely on this study? We are trying to assume that there is a rule that connects the data of individuals to the outcomes, and it is the same in Stanford and Princeton. So the same kind of hospital, the same kind of patients will have the same reaction. There isn't, for example, some environmental confounder that we are not aware of. But the difference is that the distribution of patients in Stanford, the source may be different than the one in Princeton, which is the target. So subpopulations may be over or underrepresented. This is a huge issue in statistics in general. Some of the, we run a survey, some of the source of survey is not really based on the uniform distribution. For example, you have lots of surveys that run on newspapers or digital forms. They definitely don't get the right distribution probability. Are they usable at all? And the hope is that if subpopulations perhaps are not represented in the right probability, but they are still represented, there is a chance to learn something from Stanford to Princeton. We do it all the time. The method, the prevailing method, is that of a propensity score weighting. So what is a propensity score? It is kind of this abstract notion that imagine that every individual X has some probability to appear in the source and some probability to appear in the target. And these probabilities may be different. Perhaps if you're a man, you're more likely to appear in Stanford and less likely to appear in Princeton. And the ratio is, I don't know, 1.1. What this method says is that you need to obtain unbalanced samples from both the source and the target. You're going to learn these scores. You want to learn how probability relates to each other. So you're going to learn a propensity score G from some class C. You're going to reweigh the samples from in the source based on G. And now you're going to estimate what you're trying to estimate, the outcome that you're trying to estimate on these reweighed samples. So you take the samples from at Stanford and you turn them to something that's supposed to be like this, the probability distribution at Princeton. The issue with that is that you need unlabeled samples from both the target and the source, but you need the one from the target before you do the estimation. So you're going to learn on this on the individuals at Stanford based on the sample from Princeton. Is it realistic? We may want to apply the study at Stanford for many other hospitals. We don't want to have to sample from all of these hospitals ahead of time. Perhaps we don't even know which hospitals we're going to be comparing it in the future. And perhaps we actually want to apply the study at Stanford today to 10 years from now, when the population may be different. So this probability distribution doesn't even exist. We cannot sample it now. So what we are suggesting here is this notion of universal adaptation, one that we don't need to be aware of the target when we are trying to learn the connection. The intuition is that if the estimator that we learn in Stanford is multi-calibrated, then it will directly apply to the target distribution as long as it, because it is accurate for each one of the subpopulations. So even if some subpopulation is more expressed or less expressed in the target, it will still be correct. What we are able to prove that if the propensity score comes from this class C, then a predictor that is C multi-calibrated will work just as well as using this method, this prevailing method of propensity scoring. And the idea and the point here is that we don't need the samples from the target, from Princeton, when we are trying to learn. We only need it when people at Princeton are trying to apply it, to draw inferences there. So you can use it many times for many hospitals, and including with populations that come in the future. So, and in addition, we don't even need to learn these propensity scores. It is implicit. The experiment that we have showed that this is competitive with standard methods, and at times even better, even if the propensity scores are not in the class. In fact, it's even natural that when it's not in the class, we will do better because we handle simultaneously many possible propensity scores rather than one. Now I'll get to the last application I want to share with you. I know that it is a little bit much, but I hope that each one of you found one application, will find one application that they care about, and that will be good enough for me. So this is about omnipredictors joined with Gopalan, Tauman Kalai, Sharan, and Wieder. And what is the standard method of learning? A very major method is this loss minimization. So you give an sample, as we had before in this talk, from this X and Y. X represent individuals, Y is whatever we are trying to learn. So feature space, like the personal and medical information, and the labels. Is this person test positive for COVID? We're trying to predict if people will are actually have COVID, if we will test them. We want to compute an hypothesis, T, and this T should represent various actions that we need to take. Should we send the person to be tested, or allow them to continue to attend work, or let them quarantine for 2 days or 3 days or 4 days or 7 days? What dosage of some medication we want to give. So this is the action we want to do, given that we see an individual. And the way this works is that we are defining some loss function that should measure the penalty if we are making wrong actions. If we are not sending this individual to be tested and they go to work, what is the cost of that? If we are sending them, what is the cost of that? There are various possible loss functions. For example, some popular ones are LP, so kind of some metrics of distance between the prediction and the outcome. And what then we do is minimize the expected loss. And so for a random individual, what is the expected loss in our policy? And we want to minimize it. We want to minimize the loss. One thing to note is that different loss functions may imply very different optimal actions. A classic example is that if you want to minimize L2 distance, then the mean minimizes that. If you want to minimize L1 distance, it will be the median. And in the paper, we give other natural examples. And the point, a very important thing is that if you created T with one loss function, you lost information. You cannot now go back and answer what you should have done with a different loss function. So this is where multicalibration helps. So it helps answering the question of which loss. So we may not know a priori what are the costs and what is the best loss function to use when we are learning. We may want to learn on the same data when there are several different loss functions that we will care about in the future. So, or now. So perhaps we want to base on this predictor decisions like, should we recommend daily aspirin for the patient, or should we recommend a surgery? These would have very different loss functions. Perhaps it's also not a loss function that exists now. Perhaps in the future, there will be a different operation or a different medical intervention, and it will carry even other loss functions. So when we are learning, we don't know what loss functions we'll care about in the future. If we could learn true probabilities, what is the real probability, let's say, of that the person has COVID, which we again don't know exactly what it means, then for all the loss functions we usually care about, it's easy to compute what is the optimal function, the optimal action. If you tell me that you have 20% that this individual has COVID, I can tell you if to do a particular intervention, but just knowing what's the cost of false positives and false negatives. What we want in this new paradigm of learning is to have omnipredictors. So predictors that could behave like the true probabilities, when we test them for a wide set of loss functions. So for all, again, all the loss functions we care about, essentially. And what we show is that if you have multi-calibration, it implies omnipredictors, or more formally, if you're multi-calibrated with respect to a class C, then your predictions can be used to get something that's better than anything that a predictor in C can do for you. A very strong guarantee. And now in the time of learning, we don't need to care about the loss function. We will only care about it when we use it, and we can use it many times for many different things. Okay, so with that, I want to kind of sum up and say that what I try to give you, I mean, beyond everything technical that I shared, is to give you the feeling that algorithmic fairness is both important and scientifically exciting. It reached the point where interesting things are happening, and I hope that this will kind of encourage some of you to join us. I want to say that multi-group fairness, and particularly multi-calibration, gives both meaningful fairness guarantees and also practical benefits. It has been shown in practice to do really impressive work. And finally, there is some interesting scientific and possibly later on also practical implications of multi-calibration by giving a computational perspective on the meaning of individual probabilities, an alternative to the standard paradigm of loss minimization, and an alternative for propensity scoring. And there are other applications that I didn't have the time to share with you. And with that, I think I am done and ready for questions.
All right, okay, so let's thank Omer for the great talk. I think we are welcoming questions. So anyone has any questions? So maybe I'll start with one question, I think. Okay. So I think this notion of outcome indistinguishability is kind of similar to what we have with like pseudorandom generators, these things. So are these related, or are the techniques for like PRGs useful here in this situation?
It's definitely inspired by the literature on pseudorandomness in complexity theory and cryptography. It's kind of importing it into a different area of these predictions. It's very easy to use examples from cryptography or complexity theory to actually show why a computational perspective is required.
I see.
In terms of the techniques, I mean, yeah, so we are using it for impossibilities, for lower bounds. In terms of constructions, the constructions are, because it's a very different setting, the constructions look different than our favorite pseudorandom generators. It's a new concept, so there's room for pseudorandomness experts like you to come and perhaps show us that we have missed some even stronger connection.
I see. Yeah, that's very interesting. Okay, maybe another question, which is not directly related to the talk, but just in terms of talking about pseudorandomness, I was just wondering, given the recent advances on all these PRGs, like in small space computation, so do you think it's hopeful that we will solve this RL versus L question in the near future?
Okay, so I believe so.
Okay.
So let me say, in case, although I'm sure you educated people in the past about it, but it's the question of whether randomness can be saved by using more memory, or every randomized algorithm with particular set of memory, bounded memory, can be de-randomized with a small cost in memory. And I think that we are seeing progress all the time. And
Right.
it gives me the feeling that there are still techniques and ideas to use. At points, I would tell students that we are trying to admit to Stanford that my plan is not to retire until RL equals Z is
Okay,
proven,
I see.
and therefore that we need their help. And so, yeah, I wouldn't be surprised if it will be open for another decade. I wouldn't be surprised if tomorrow somebody proves it.
I see.
Or perhaps I will have to retire without.
Okay.
It's unpredictable, but I feel that it is within reach. I don't feel that we exhausted this research, and I think, and talking with you, I'm probably preaching to the choir, that this is one of the most exciting problems within complexity theory that is within reach.
Yeah, I definitely agree.
Okay.
I have one question.
Yeah, go ahead.
Yeah, so yeah, great talk. I think I have a question about adaptation work, because that's quite close to my area. So traditional domain adaptation method, they will really suffer from if the target is very far away from the source. And then the question here is like whether multi-calibration also suffer from that. Like, does that the performance will be related to like how far away the target is from source, or is not? It's quite robust to that. So yeah.
So that's a great question. What we are trying to do is compete with propensity scores, which of course will do very badly if there is a big difference.
Right.
There is a hope that we can do a little bit better, but if you have no representation of a population, and if things for this subpopulation really operates very differently than for other populations, other part of the population, you just don't have the information. So definitely in terms of what we can prove, we cannot prove anything. In practice, there are connections. By the way, other people in our collaborations on fairness have different approaches. For example, approaches that try to take the data and remove attributes on which the two distributions are very different, and try to learn some essence that is correct in both areas. I mean, it's an extremely important area, and I'm not trying to claim that we are revolutionizing all of it. I think what we're trying to do is compete with this very important method of propensity scoring. And I do feel that in practice, we will do probably better than propensity scoring in some cases. But that I cannot, I mean, I need more experiments to substantiate it.
I see. Maybe a follow-up question to that. So I think it's also related to my, so I think I'm also interested in fairness, and that you mentioned the multi-calibration is one additional layer of guarantees that are kind of on top of this bias of data. So a bias in the training data. So I'm just thinking like whether these two can be totally separated. Like, can we really get the fairness without dealing with the bias of data? I guess definitely have multiple calibration would be better, but yeah, how is this two component correlated with each other? Right,
they are correlated. For example, okay, so there are various sources of discrimination biases in the data. For example, one of them is that exactly this notion of underrepresentation in the data. And that's one place where multi-calibration almost immediately makes some important benefit. One place in which experiments show that it does very well is with respect to gender shades. The gender shade example, and this is one place where because there is some underrepresentation, but because of multi-calibration, you're actually doing pretty well. There are, of course, other things. For example, the labels may be incorrect, and perhaps more incorrect for the protected sets. We may have less attributes, less information for the protected set. So again, there is nothing in algorithmic fairness that would capture everything. Still, I want to say that at times what we're trying to do, right, so that's, I kind of hinted, and this is an ongoing work, that that multi-calibration can be used as the basis for affirmative action, which is more refined. So there is some philosophic understanding, I think in many areas, not outside of CS, that if you want to correct things, it's really important to understand how things are now. What is the world as we observe it? And so one question that we can ask when we search nurse in Google images, do we want to see equal representation of different genders, or we want to see reality? It's a big question. So in some sense, you can think about multi-calibration as capturing the situation as it is, and the more information we have, the better we can try to correct. And finally, you can have multi-other things. It doesn't need to be multi-calibration, so multi-balance, and we have a particular notion that tries to take this idea of fairness through awareness, metric fairness, which has some practical problems with it, to make it more practical through so we have multi-metric fairness in this sense.
I see. Yeah. I think there are a lot of things to be done in this area. Yeah, very interesting talk. Thanks.
Thank you very much.
Okay, any other questions? All right, so maybe if there's no questions, then let's thank Omer again for the great talk.
Thank you very much for inviting me. Yeah.
Sure, unfortunately, it's you cannot be here because of pandemic, but maybe sometime in the future.
I'll be delighted.
All right, okay, thanks, Omer.
And thank you to everyone that came today. We really appreciate everyone's attendance.